Well, it's still at 0. So there we go.
Yeah, but it worked. Usually I have to go over there to click it. It's very strange. But on the worksheet, the interesting piece is that first one. Normally, when we have a piecewise defined function, normally we are going to have a piecewise defined derivative. So if we start with a function like the absolute value of x, we know that it has two pieces. And when you find the derivative of your piecewise defined function, you do it piece by piece. So your derivative is a piecewise defined function. And the interesting thing about that one that we had on the worksheet is that when we have natural log, I think it was absolute 1 minus x, when you take the derivative here, so this is a piecewise defined function, it's equal to either that or that, depending on whether what's inside is positive or negative. It can't be 0 though, because natural log is not defined at 0. And when you take this derivative here, oh, and I forgot the ln over here. There should be an ln in front of each of these. Smooth. Come on, get all of it. Ah! Okay, there should be an ln. So, oh my gosh. So if what's inside is not negative, we're going to have just ln of 1 minus x. And if what's inside is negative, you have to put the negative inside the absolute value in here. Oh my gosh, I gotta get on the ball here. So the absolute value is on the inside here. So it's the absolute value part that you either erase the absolute value or you multiply what's inside the absolute value by -1. And then when you find the derivative here, you will see that the derivative of each piece is actually the same.
Gotcha.
Right? The derivative is no longer piecewise defined. The derivative of this top one is 1 over the inside, but then you multiply by the derivative of the inside, which is -1, and you could put that down here, right? You can put it in the denominator, and that's going to be the same derivative as that.
Gotcha.
So that's the whole point of that first one, is that sometimes you can have a piecewise defined function that doesn't have a piecewise defined derivative. It's just one function. So that's the interesting part of the first one. Okay, so let's go ahead and do a sample example of all of these, or as many as we can get to. Reverse chain rule, that's going to be a fundamental part of pretty much all the integration going forward. It's very common to have a base or an angle or an exponent that's not just x. It's more complicated than just x. And if it's more complicated than just x, we use reverse chain rule. You could use substitution if you wanted, but again, we've seen that that's just a lot more work. So reverse chain rule, we take the base, we add 1 to the exponent. When you add 1 to -4, you get -3.
Are you sure?
Not -5. And we divide by the new exponent. And then the reverse chain rule piece says also, look at the base. Right there, there's the base. Take its derivative and divide by the derivative of the base. And then we have a constant of integration. So you don't have to on the exam, but a lot of times, like homework systems would prefer you to write with no negative exponents. So you could write it like that. Hopefully this is making a lot of sense by now. We've done a ton of reverse chain rule. Any piece of that needs a little extra explanation? Okay, so how about this one? Here we have an integral, and we see negative exponents. The moment you see a negative exponent in an integrand, you should think, let's get rid of the negative exponent. And there is a Zamboni,
A little early today.
a little early. The negative exponent can be eliminated in a couple of different ways. There's the sort of old, when you first learned about negative exponents, you learned that you could just push this into the denominator of this local term right here, which you can do. But in calculus, usually what we do is the more clever simplification, and we multiply by e to the exponent without the negative. So we're going to multiply through the numerator and through the denominator by whatever the negative exponent term is with that negative removed. And when we do that, in the numerator, we have e to the 4x times e to the 4x. Powers with the same base, we add the exponents. So we get e to the 8x. And in the denominator, recall that you must distribute. This is going to go to each term. So we have e to the 4x again times e to the 4x, just like the numerator. So we have an e to the 8x. And then with the second term, e to the 4x times e to the minus 4x, you add the exponents and you get e to the 0. E to the 0 is 1. So these two multiplied together, that and that, become 1. All right? And then we go from there. What's the next step?
Log form.
Log form. Right? The derivative of the denominator is almost the numerator. The derivative of the denominator, derivative of negative 3 is 0. Derivative of e to the 8x is itself times 8. So we're going to put an 8 up here, and to balance that out, we put an 8 in the bottom. We've just multiplied by 1. We've now put it in logarithmic form. The 1/8 is out in front. And then we have natural log absolute value of the entire denominator plus c. So that's another thing that we will see, that we have seen a lot of and will continue to see a lot of, integrands that are in log form. What was that?
Oh, how's that log form?
How is it log form?
Yeah, I can't.
So the derivative of the denominator is now the numerator.
Oh, I see it now.
You see it?
Yeah.
So if we can put it in that form where the derivative of the denominator is the numerator, we immediately get that. And recall that, right, when you integrate 1 over x, isn't that log form? Right? The derivative of x is 1. That is log form. They didn't call it that in Calc 1. In fact, they don't call it that in any book, but we call it log form for an obvious reason. Every integral that integrates to a log has that form. So we'll call it log form. We always get natural log of the absolute value of the denominator.
Would you need the absolute values on that?
Yes. Because this function is not restricted to be positive.
I mean up top.
Up here,
Yeah.
Still do, because
This-
yeah.
yeah, 0 is a great example. If you plugged in x equals 0, you would have e to the 0, which is 1. 1 minus 3 is negative.
Okay.
And we can't take the log of a negative number. If we look at the graph of the logarithmic function, looks like that.
Okay.
So log is not defined for anything less than or equal to 0. Yeah, log of a negative is not imaginary, it's just undefined. Any other questions on that? A lot of these little things are good to ask about, because you want to be really familiar with logs and exponentials as we go forward. Those functions are so common.
Yeah, can you, sorry.
Yeah, oh,
Can
no
you
problem.
explain the multiplying by 1?
Yes, which part of it? Like how I chose it? or how to actually execute it.
I guess one more step over. Yeah, there.
Oh,
Like how to execute that, yeah.
the 8/8 or the bottom?
8/8. Why?
Okay, so when we take the derivative of this right here, the derivative of this constant is 0,
Right.
and the derivative of an exponential is itself
Over 8.
multiplied by the derivative of the exponent. And the derivative of that exponent is 8. So that part right there, we're using the chain rule down here when we differentiate. So the derivative of e to the 8x is e to the 8x, and then the chain rule part, you multiply by the derivative of the exponent.
That's it.
So the chain rule part, you're always multiplying by the derivative of the exponent or the angle. Welcome. There are plenty of empty seats. Some people have dropped, believe it or not.
Shocking.
Shocking. And I can't remember your first name?
Amber.
Amber? Amber's in the online Calc 2 class, but wants to have some classroom experience, and we have plenty of seats, so we said, come on aboard. Now, if anyone wants to jump into the online class, not the move. So that's called the chain rule part when we come up with this as our derivative. But the 8 was missing, so we throw the 8 in there, and we balance that out by multiplying by its reciprocal. So we balance it out by multiplying by 1/8. So as soon as we do that, we're in log form. Derivative of the bottom's the top, so we get natural log of the absolute value of the denominator.
Now, when you're doing the integral of an e to a power, it's e to, so it would be e to the 8x divided by 8 though, right?
Right. So if we had just a random thing like this, so if we had integral e to the 4x, the integral of an exponential is itself. So we do that first, and then when we're integrating, we don't use chain rule, we use reverse chain rule, so we divide by that 4,
Yep.
which is going to plop it in like that. Versus, the derivative of this, when we take the derivative of this, the derivative of an exponential is itself multiplied by the derivative of the exponent. So that one is called the chain rule, and that one's called reverse chain rule.
No plus C on the derivative, right?
No plus C on the derivative, thank you.
Just double checking I'm not.
Yeah,
missing
no,
something.
yes. Yeah, no plus C on the derivative. No plus C.
Becomes zero, in fact.
Yeah, the C is 0. All right, let's go for a completion of the square. So here we look at that integral. We see the denominator is a non-factorable quadratic trinomial. And if we have a quadratic that is factorable, what would we do?
Factor and do.
Maybe tricks.
Nope.
If it's factorable,
PFD.
PFD.
Partial factor.
If we have a factorable quadratic in the denominator, we factor it and then we can use partial fraction decomposition. That would be the easiest way. Certainly there are times where we have a factorable quadratic in the bottom. We could use trig sub if it was like an x squared plus 4. We could use trig sub, or factorable. X squared minus 4. If it's factorable, you could use trig sub, but PFD is going to be faster usually than trig sub. But if you're good at trig sub, you could certainly do it with trig sub. But here we have a quadratic in the denominator, not factorable, so we complete the square. That's going to be our technique. And when we complete the square, we take that middle term right there, look at its coefficient, divide by 2 and square. So what do we need to complete the square for these two terms? What do we have to, what's the constant that it needs? It needs a 1,
Plus one.
a plus 1. Divide by 2 in quantity squared, so it's positive.
Minus one is the constant is.
The constant is plus 1. And the way we typically think of this here is just grab a 1 from that constant out on the right. Now we have a perfect square trinomial. This right here is a perfect square trinomial. It's a trinomial that can be factored into x minus 1 quantity squared. So we have x minus 1 quantity squared plus 49. Now we're staring at a really classic sum of squares in trig substitution, right? When we see a sum of squares or a difference of squares, we think trigonometric substitution. That's the sort of best technique usually. Now, the strategy that we've been using in this class is to not only get it into the sum of squares or difference of squares notation, but to make it with a 1. We want our constant to be 1, and the reason is it makes for less memorization in the long run. And so we're going to factor out that 49 to create a constant of 1 there. So that 49 is coming out in the denominator. So we're factoring out a 49. So we've got that. And you're looking at this and you're seeing that there's not a 49 here. Well, we can put one in. And the 49 that factors out is that one. So that's coming out to the front in the denominator. We're left with a 49 in the denominator here. And we want to turn that into a square. So we write that as x minus 1 divided by 7 quantity squared. Now we've got the nicest possible form for us. Sum of squares with a 1. And what form is that in? Arctangent. Exactly. We could use trig sub, but we don't need to because it's already in arctangent form. Right, we already know that the integral of 1 over x squared plus 1, that is arctangent of x. And that's the form it's in. Now we do have to do one little thing called the reverse chain rule, because this is not just x. Right? That's 1/7 x minus 1/7. So that's a linear expression, and we will have to do reverse chain rule, or if you have a lot of time on your hands, you could do U substitution if you wanted. But we've seen that there's no need to do U substitution when you have a linear substitution. So this is going to be 1/49. I'm going to leave space for the reverse chain rule. We know that we're going to get a constant from the derivative of that. So it's arctangent of whatever's in the parentheses, so x minus 1 over 7. There's going to be a plus c we're integrating. And what is the derivative of that yellow quantity in there? 1/7. Right, the derivative of this is 1/7. Is there any question on that? If you want to, think of it like this. Think of this as a distribution of the 7 into the numerator. So it's just a line, right? It's 1/7 x minus 1/7. And the derivative of a line is the slope. So we're going to divide by 1/7, which means multiply by the reciprocal. So we multiply by 7 over 1. That make a lot of sense? Or no sense? Or something in between?
Just enough to get you through the day.
Just enough. So there we go. That is how we would integrate that. Any step there you're wanting more explanation on?
Isn't the 1/7 x minus 1/7 squared though?
It is, but when we do reverse chain rule, we're looking at the quantity that's inside.
Okay.
So it's just like, let's suppose that we were looking at sine of, let's suppose we had, let's make this like sine cubed of, let's make it different. Let's make it 5x minus 3, something like that. If you were going to differentiate this, so let's suppose we're taking the derivative. When you differentiate this, your chain rule part is just with what's inside the angle. You don't deal with the 3 for the chain rule part. And it's the same thing for integration. You only are dealing with what's in the parentheses. So here, when we differentiate, we're going to end up getting a 5 out in front. Right? So the chain rule or the reverse chain rule is just with that parenthetical quantity. It's what's inside the parentheses. It's not, the power doesn't have anything to do with the reverse chain rule or the chain rule. Let's jump to integration by parts. So integration by parts. Remember that at its core, integration by parts is essentially a reverse product rule. Like, that's kind of how we think of the power of integration by parts is for products, when you're trying to integrate a product. Now, we've seen also that it applies to some really interesting integrands like inverse tangent, natural log of x. But at its heart, we think of integration by parts as a reverse product rule. The product rule allows you to differentiate a product. The reverse product rule allows you to integrate a product. And so integration by parts is a reverse product rule. And we are always going to break apart this integral into two parts. So we've got these two functions, x and e to the 4x, and we have to group them. One of them is going to have to go with u, and one of them is going to have to go with dv. The dx will always go with the dv. And so we've got this kind of as our basic starting point. And then we say, okay, which goes where? Well, we generally, for the dv, pick the most complex part that's easily integrable. E to the 4x is more complicated to integrate than x. And so that's going to work out really well here. And we'll put the x over there. So now we've subdivided the integrand into two parts. And we can do what we need to do now. Another thing to keep in mind is that if you were to put the e to the 4x with the u, and then you differentiated it, you would still have an exponential function there. And the x over with the dv, if you integrated it, you would get x squared over 2. So you'd be bumping up the power of x and making the integrand more complicated. So that's not going to actually work if you did it the other way. But this idea of putting the most complex part that you can integrate here works 95+% of the time. That's a good way to think about it. You know, and if we did do it the other way, eventually you're going to see that it's not the right way because the integral is going to be more complicated, and so then you go back and you switch. Okay, so then on the left column we're differentiating here, so this is going to be du equals dx. All right, let's integrate this. What's the integral of that?
1/4.
1/4 e to the 4x. So the integral of this exponential is itself, e to the 4x, divided by the derivative of its exponent. And now we can apply integration by parts formula, ultraviolet voodoo. So UV, there's our ultraviolet part. So that's going to be 1/4, and then we have an x, and then we have an e to the 4x, so there's our first term. UV minus the integral of VDU. VDU is the bottom row. There is the voodoo, VDU. So we'll integrate that. Let's see, what do we end up with? Just 1/4 e to the 4x dx. So one iteration of integration by parts, not too bad. And now we have an integral. This is where we make our assessment. Did we pick properly? If this integral is easier than the original integral, we definitely picked properly. If it's equivalent, you're probably dealing with the whole twist thing. If it's worse, you picked incorrectly and you'd have to go back and switch your functions. And this is integrable now. The integral of an exponential is itself, so we're going to get an e to the 4x. But then we have to divide by 4, so what's that coefficient going to be?
1/16.
1/16 plus c. Yeah?
What if you have to do 3 parts?
then you would do 3 parts.
How'd that work?
One after the other. So if this power on the x were a 2, so if it was x squared, the first integration by parts would leave us with an integral here that looks like that, and then we'd have to do integration by parts on that to get what we just did here. If the power on x were a 3, we'd have to do integration by parts 3 times.
Or what I meant is like, well, what if we had like x e to the x sine x?
Oh, if you had a double product?
Yeah.
So if we had, okay, so if we had 3 functions in there, you'd have to break it into 2. So if you had something like x e to the x sine x, you would have to group the x with one of them and then go from there. That would be extremely complicated though. You'd have an integration by parts sort of inside an integration by parts. Different than just doing integration by parts twice. That would be a hard one. So we are only going to see products where we can separate them into 2 distinct functions. If you had 3, it's just going to be a lot more work. You could do it, but it's going to be a lot harder. I'll give you one just for fun.
That'd be a mean exam question.
Right, it would be a mean exam question. So expect it.
ideas.
Right? Whoa.
I'm starting to get an idea.
Yeah, that could be a cool extra credit problem though. Right? Is there any piece of that that we're not sure about?
I'm gonna have problems. That's where you break down go-go gadget.
All good?
It's all good, man.
It's all good, man? It's all good, man. Integration by parts, piece of cake.
We're saving all our money.
All right, so integration by parts, let's do it with a twist, just because that's how we roll.
Hypothetically, on the twist, or on the test you didn't realize and you just handed it a full sheet of it.
So integration by parts with a twist, the nature of integration by parts with a twist is when each of the 2 functions has the property that when you differentiate or integrate, it just sort of is a cyclic kind of process. Like with the x squared or x cubed, you can just keep differentiating down to 0 eventually. But with e to the x and cosine or sine, you can't. And so that's how we sort of have this heads up that, oh gosh, it's going to be integration by parts with a twist. And with integration by parts with a twist, it doesn't matter what you pick for your u and your dv. You can put either function with the u or with the dv. It doesn't matter. And some folks will, maybe differentiating a trig function is easier than integrating. So if that's the case for you, maybe put the trig function with the u instead of the dv. It's not going to matter. Okay. I'm comfortable integrating the trig function though, so I'm going to put it with the dv. So we'll differentiate the u. We'll get du equals derivative of an exponential. 3e to the 3x, yes. Good. It's itself times the derivative of the exponent. Yay. Integral of cosine 2x?
Negative sine of 2x.
Nope.
1/2 sine.
Yes. The derivative of cosine is negative, but the integral of cosine is positive because the derivative of sine is cosine. if that made sense. So, and this is a really common thing, is to get that sort of, not to belittle dyslexia, but that kind of dyslexic thing where you put the minus when you shouldn't have put the minus. You can always double check, right? You integrated to get to v, so you can differentiate your v to get back to the dv. So you can always double check. And if you differentiate sine of 2x, the derivative of sine of 2x is cosine of 2x times 2. And then if you take the times 2 and multiply it by the half, that becomes a 1, and you get back to where you started. So if you have a tendency to do those kind of things where your derivatives aren't 100%, double check. You can always double check. So now we're going to do the integration by parts. This is going to be u times v. This is the ultraviolet part, uv. So we have that. There's our uv minus the integral of v du. So if we put all that stuff together, it looks like a 3/2. And then in e to the 3x multiplied by sine of 2x dx. And we're at that new integral spot, we look at it, it's the same difficulty as the original, which will happen when you have integration by parts with a twist. It's not easier, it's not harder, it's the same. We're going to have to go with the twist. And as soon as we recognize that we're going to have to go with the twist, we remember that there's that algebra thing, which is what I'm calling the twist, where we have to combine like integrals. So we have to call this integral something. And so I think that the easiest thing to do is call it either I, or what we've been using is omega. So we're going to say that this original integral is equal to omega. And if we want, we could put a little space here and just move this over and say, okay, so if the original integral is called omega, then we now have this. That's where we're at. Let's put the omega here. So we're going to call the original omega, call the original integral omega. So now we have that. Omega is equal to that. All right, we have to do integration by parts again. So let's go ahead and let's have some foresight here. So this constant you could factor out to the front, but what we've seen is if you factor it out to the front, you end up with this massive, huge set of parentheses that you then have to distribute it back across eventually anyway. So it's usually easier to leave the constant inside. And speaking of that, we have a minus out in front. We still are going to have to do a distribution of the minus with that minus out there. So the easier thing to do that we've seen is that if you actually put the minus on the inside and make it a plus out there, that will make the distribution of the minus irrelevant. It's all going to come out in the wash. So let's go ahead and do that. So we're going to end up with this stuff in front, and then we'll set up our second integration by parts. So that's where we're going to be at. Then we're going to do plus u times v minus integral of v du. So let's see what happens. So, and the other thing we want to do is keep our pattern consistent here, or we'll just undo what we did, which we don't want to do. So by that I mean if you let u be the exponential up here, then you want to let u be the exponential down here. So I'm going to treat this as one function here, negative 3 halves e to the 3x, and then there's our second function. So let's put the whole first thing over here with u, so negative 3 over 2 e to the 3x. And then for the dv, we're going to put the trig function, sine of 2x dx. This we can differentiate pretty easily here, so du is going to be minus 9 halves e to the 3x. So the derivative of an exponential itself, e to the 3x, multiplied by the derivative of the exponent, so we multiply negative 3 halves times 3. And then over here we integrate. The integral of sine is minus cosine. And then we have to do reverse chain rule. We have to divide by 2 or multiply by half, however you want to write it. All right, so any questions up to this moment? So now we have a plus out in front, which is great. We don't have to deal with distributing a minus. We can just do our uv minus integral of v du, and if a negative pops up, it pops up, and it's fine. We don't have to do a combined thing. Okay, so u times v. Oh, that's positive, right? Negative times negative is positive, no sweat. So we have 3 over 4. And then the exponential part is e to the 3x, and then the trig part is cosine of 2x. So there's UV, ultraviolet, minus the integral of v du. Let's see, so if we multiply the constants, we get 9/4. And oh look, so there's a minus and a minus. So we're subtracting off v du. V du is positive, so what goes in the integral is positive. So 9/4. E to the 3x is the trig part, excuse me, the exponential part. The trig part is cosine of 2x dx. Perfect. And this, of course, is omega on the left, right? Omega is on the left side. And here's where we do our twist stuff. We see that that integral there matches the original integral. It's just a multiplier, a constant times the original. So this can be rewritten as, let's make sure that it's clear, we'll just rewrite this line with the one change before we do our twist. So before we do the twist, we are doing an algebra step. We're saying, let's factor out the 9/4, and then the integral of e to the 3x cosine of 2x, that's what we're calling omega. And now we are back to algebra 1. We've got a one variable equation, one variable in omega. We're going to treat it like a one variable equation in omega. So we're going to add, what are we going to think of this coefficient as so that we can combine these two omegas?
4/4.
Yeah, 4/4. So then when we add, when we twist these omegas together,
13.
yep, we get 13/4 omega. And when we do that, the moment we move the omegas to the left, we need to introduce something on the right-hand side.
Plus Charlie.
C. What was that?
Plus Charlie.
Plus Charles? We'll tell Charles that he's gained new fame in Calc 2. He has become our constant of integration substitute. We will add Charles von Thagen as a constant of integration. And then our final step, our goal was to figure out what that integral was, and the integral is represented by our omega. So we multiply both sides by,
The reciprocal 4/13.
yep, by 4/13, the reciprocal of the left side, so 4/13 is coming over. We're going to end up with 2/13 e to the 3x times sine. And then when 4/13 comes over here, the 4's cancel, so we'll have 3 over 13. Did I say that right?
Yes, yeah, 3/13.
3 over 13, yes, thank you. And then plus Charles. All right.
And if we did it the other way, should your answer be the same or would it be?
Yes, it will be the same. It'll actually be identical. The sine would be over here, though, and the cosine would be over there. But it would be identical. So it's not like, did we, or was it you and I that looked at the one where the answer was totally different when we did a power of sine and cosine? Was that us or was that someone else? Oh, maybe, was it Chris? Was it us?
I don't know. There's on the worksheet.
What's that?
The one on the worksheet.
Maybe.
There was one on the worksheet where you had.
Oh, yeah, that's right. On the worksheet, there's one like that. If you have like a sine cubed and a cosine to the fifth, depending on what you let u equal, you'll have an answer that looks totally different. But if you were to graph them in Desmos, they would be identical except for a constant.
Yep.
They'd just be shifted. And you could get from one to the other if you did your Pythagorean substitution. If you see a sine squared, you could replace it with a 1 minus cosine squared, or you could replace cosine squared with 1 minus. You could get to the other one if you had to. All right, let's bounce to shells. So find the volume of the solid that is generated when the region bounded by e to the negative x and the x-axis on that interval is revolved around that line. Okay, so first off, and I saw this on the first exam, you should be able to graph exponential functions. Exponential functions have asymptotes. They don't go through the origin.
What's an exponential function?
It's one of those functions that grows or dies really fast. Does this one grow or die fast? Yeah, this one's,
It's my bank account.
this one, this is your favorite kind?
Yeah.
Quick death. So exponential decay. Think about in your head, if you plug in x equals 0, it goes right through 1, right? E to the 0 is 1. And then as x gets bigger, so if you're thinking about this, if you wanted to, you could write it as 1 over e to the x. As the x is getting larger and larger, the denominator is getting larger and larger, so the fraction values are shrinking to 0. So it has that look to it, exponential decay. All right, and now we're told that we're only going to look on the interval from 0, so here is 0, the y-axis, over to ln of 6. So we'll suppose that ln of 6 is right here. So this is the region that we are focusing on right there. And that is going to be revolved around the line x equals natural, oh, that line itself, right here on the edge. Okay, so we're going to think about that line right there, and we're going to rotate about that. So now we're told in the problem that we're going to use shells, but hopefully when you look at that region and envision it being rotated around natural log of 6, that's the natural choice. Because this region here is not horizontally simple. If you were to draw a horizontal line there or a horizontal line there, they have different right boundaries, so that's bad. We want to pick an element, an integration element, a little mini rectangle. We want to pick one that has the same upper and lower curve all the way through, or the same right and left all the way through. So we definitely want to use an integration element that's vertical. And then we ask ourselves, okay, well, if this is a vertical element and this line is vertical, if we're going to do a rotation, what's the geometric shape that we're going to create? We're going to create a cylinder, cylindrical shell. So we're going to use the shell method. And the area of a shell, it's just a cylinder, so its area is 2 pi RH. That's the area of a cylinder.
It's a cylinder without a top and bottom.
Correct. Yeah, when we say cylinder in math, we mean there's no top and bottom on it. They would have to, like in Calc 1, if you're doing the surface area of a cylinder, they would have to tell you that we're going to include the caps. But if we just say cylinder, so when you get into Calc 3, you'll generalize the concept of a cylinder. And a cylinder is something that's created with a generating curve and rulings. And rulings are, like you think of paper, those rulings. And so if you have a circle and you choose a vertical ruling, you pull that circle along the ruling and that creates a cylinder. So you can have a parabolic cylinder. If you have a parabola down in the xy plane, then you pick your ruling and you pull that parabola along the ruling. If it's vertical, you get a vertical parabolic cylinder. Even though it's not closed, still considered a cylinder. A cylinder is a curve that's pulled along a line. Your ruling could also be diagonal. So you could have your parabola down here and pull it sort of diagonally and have this cylinder, this parabolic cylinder that's sort of skewed. So in general, in math, when we say cylinder, there's a generating curve and a ruling that you pull the curve along. All right, which you'll do in Calc 3. So there's the area of our shell right there. So then we come down here and we have to decide what R and H are. And so we look at that distance right there. That is the radius of the shell. So if you imagine this vertical integration element rotating around, it's going to create a cylinder, and the distance from that vertical integration element over to the axis of rotation, that's going to be the radius. And this radius is a horizontal distance. And anytime we are dealing with horizontal distances, we do the right x value minus the left x value. That's how you get a horizontal distance, big X minus small x. So the right x is ln of 6. The left x is just x. So there is the radius. So the radius right there, that is the radius. That's this distance across right there. Right x minus left x. Okay. And then the height,
This is the function.
the height is the function. It's e to the negative x. Right? This height, the height is right here. It's whatever that distance is from the x-axis up to the curve. Well, that's what the curve measures. If you plug in an x value, it tells you what the distance is to the x-axis. So that is the height of our corresponding cylinder. So there is the area of our cylindrical shell. And then to get volume, you integrate area. And we're going to integrate area from 0 over to natural log of 6. And the 2 pi is a constant. It can certainly come to the front, so we can put it out in front if we want right away. And let's distribute that e to the minus x business. So we're going to have natural log of 6 multiplied by e to the minus x, and then minus x e to the minus x dx. The first part of this integral, this we can integrate immediately. That's just a constant times e to the negative x. E to the negative x has an antiderivative that we know. So that we can do right away. What technique do we have to use for this product?
Integration by parts.
Yeah, integration by parts. It's a reverse product rule. So we'll do that. So this 2 pi is going to be way out in front, big brackets. And then this part gets integrated. So this is going to be natural log of 6. The integral of e to the negative x is itself divided by negative 1. The derivative of the exponent is negative 1. We reverse chain rule, so we divide by negative 1. And now this gets evaluated on the interval 0 to ln of 6. Minus, over here, we're going to have the integral from 0 to ln 6 of x e to the minus x. And again, if we wanted to be clever, we don't have to be, but it actually makes our work easier. If you put this minus on the inside, then we don't have to worry about distributing a minus in the end. If we have plus some business, we can just figure out the business. Right? We don't have to think about distributing the minus afterwards. Super easy to make that mistake. But it comes out fine as long as you have your brackets and everything in the right place. All right, so now we have 2 pi. And in here, we can pause and just evaluate from 0 to natural log of 6 later, because we're going to have to do that anyway. We can just do it all at once. Doesn't matter. You can evaluate it right this moment if you want. It's whatever your preference is. I'm just going to wait and get this other integral taken care of. So let's come over to this other integral. So that's going to be an integration by parts, so we have to have a u and a dv. And we've already seen this type of integral today. We want to have the u be what?
Negative x.
Negative x, because the derivative of that's going to take that power of x away. And then we'll put our dv over here. The derivative of negative x is negative dx here. Integrate over here. Reverse chain rule. We get that. So down in here, plus, and u times v is positive. So we're going to have an x e to the negative x, and this is evaluated 0 to natural log of 6. We're just going to do it all at the very end, though. So there's the ultraviolet, UV, minus the integral, same limits of integration, of v du, that's the bottom row. Negative times negative is positive, so what goes in the integral is positive. So that's going to be e to the negative x on the inside of the integral, times dx. Close off the big brackets. So now we've done the integration by parts piece of it. And we're ready to roll, so we're going to have 2 pi times a bunch of stuff. So let's figure out all this stuff in here. So that and that. These are just waiting to be evaluated. And we can take off this evaluation bar because that's going to be the same evaluation bar that we're going to use here. So this is minus, the integral of an exponential is itself. Divide by -1, which makes that positive right there. Makes that positive. And then this whole thing is evaluated from 0 to natural log of 6.
And does it matter if the evaluation bars are inside the bracket or outside? Or
Doesn't matter. Yeah, you can put it
as
either.
long as they're there?
As long as they're there somewhere, yeah, it could be either. I mean, with the outside, it's clear it's the whole thing. I mean, it's clear anyway on the
It's all
inside.
X's? Yeah.
All of them are X's. So let's go ahead and do this evaluation. So first, let's plug in that upper limit of integration. So ln of 6. So let's think about this. When we put the ln of 6 there, we know that e and ln are going to be canceling each other out. They're inverses of each other. But we've got a minus in front. So e to the negative natural log of 6. So e to the negative natural log of 6. We need that coefficient to invoke superpowers and fly up as an exponent. And so when the e and the natural log cancel, we will get 1/6. 6 to the -1, that's the reciprocal of 6. These functions are canceling. So substituted in there is going to give us a 1/6.
A negative 1/6.
Nope.
With the, well, the negative.
Yes, that negative,
Oh, yeah.
but and also this ln
And
6 too.
then
Yeah,
ln6,
yeah.
Never
That part will be positive,
That's
so we'll end
positive.
up with negative natural log of 6 all divided by 6.
Yep.
Which is, I think, what you were saying.
Yeah.
Okay, so we got that. And then over here, same idea, right? We're going to have the natural log of 6 coming in for the x here. The natural log of 6 coming in up there puts that piece of it over to that. So we're going to end up with natural log of 6 over 6. Ooh, that's convenient.
They cancel.
They cancel.
It's a miracle.
And then over here, oh, we end up with the same type of thing, 1/6. So that is the upper limit of integration. Now we plug in the lower limit of integration and we subtract off everything. So in here, e to the 0 is 1. E to the 0 is 1, but we're multiplying by 0. And here, e to the 0 is 1. So we're going to have minus natural log of 6 multiplied by -1. We're subtracting off this. And then subtracting off 0, and then subtracting off 1. So these guys wipe each other out. And the only thing left to do is combine those little constants. And 1 over 6 minus 6 over 6 is -5 over 6. Plus natural log of 6. Okay, there is a long-winded way to find the volume of that shape. Any piece of that you want to ask about? Not sure about?
And so any constant on the ln of something in an exponent, you always have to pull it up into the exponent of the thing inside before you can, yeah.
Before we can invoke the inverse property rule to annihilate each other, the e to the x and the natural log.
I definitely learned that at some point and then completely forgot it. So
Yeah.
That's fun.
Yeah, it's nice. So you need to know your laws of exponents to get that, the right form so you can collapse the e in the natural log. All right, let's get to integrals of powers. So first we'll do powers of sine and cosine. So powers of sine and cosine, this is the easier of the two powers. The tans and the secants are a little more complicated. But for sines and cosines, all we have to do is look for an odd exponent. If there is an odd exponent, we're going to target it. And so when we look here, we've got a cosine cubed of x. So we're going to target that one. And so the idea is that we're going to pull one off from that odd power, which will give us an even power. If we pull one off, it's going to be even. And even powers of sine and cosine can be converted really easily with the Pythagorean theorem. Sine squared is 1 minus cosine squared. Cosine squared is 1 minus sine squared. So we can convert easily. So with an odd power, we pull one off. So I'm going to leave the front function alone. So we've got 4 times sine to the negative 3/2
Did you
of
pull
x.
that 4 out?
4 can come all the way to the front if you want.
Okay.
Yep, you can. And then here, we've got a cosine squared. And then we pulled off 1 cosine. So if you have an odd power, you pull off 1, and you at least mentally think of it as part of the differential. So we're going to just think of that as the differential. And that indicates what our strategy is going to be. What are we going to let u equal?
Cosine x.
Nope. Sine, so that its derivative is the cosine. So the piece that we group with the differential, that's our target derivative of whatever we're going to let u be. So if we let u be sine, then bang, its derivative is going to get us cosine x dx. And so the whole idea with this odd power is that when you pull one off, you know you're going to let u be the other function. And if you left an even number behind, it's easy to convert with the Pythagorean theorem. So then we're going to have, so we can pull the 4 all the way to the front. So we're going to have sine to the negative 3/2 power. And then this is going to be 1 minus sine squared. And so now we've converted everything over to sines except for this cosine that we think of as attached to dx. And that puts us in our position to let u be sine of x, and du will then be cosine of x times dx. So the whole idea of pulling that off is that we're going to let u be the function that has whatever's in the red box as its derivative. So we'll let u be sine. So this will be for integral. That's going to be u to the negative 3/2 multiplied by 1 minus u squared multiplied by du. It's always a lot easier to switch over to u's before you start distributing. We will have to distribute. This is going to, that is going to be distributed to here and here. You could do it with the signs if you wanted above, but that's just a little more work.
You could theoretically do integration by parts here.
You could. I dare
If
you.
really wanted.
Yeah, if you really want, you could do integration by parts here. So when we distribute, we're going to distribute to 1 and get u to the negative 3/2. Negative 3/2 is minus 1.5. We add 2, we get positive 1/2. That's our second exponent. And now we're good to go. We have everything in easily integrable form. So we'll use the power rule. Power rule for integration, not the power rule for derivatives. Power rule for integration, we add 1 to the exponent. So we're going to get negative 1/2. We divide by negative 1/2, which means multiply by negative 2 in practice. And then over here, add 1 to the exponent, we get u to the 3/2 multiplied by the reciprocal plus c. And the last step, distribute the 4, back substitute. For u, we said that u was sine of x. So this is going to be negative 8. Sine of x to the negative 1/2. So that's the square root of sine of x in the denominator. Minus 8/3 times sine of x raised to the 3/2 power plus c.
You go back up.
Yes.
When you're distributing the negative 3/2 to the 2, so negative 1.5 times
Plus.
negative 1.5 plus 2.
Yes.
Because you're adding that. Okay.
Yep. So exponentials with the same base, you add the exponents. X squared times x cubed is x to the 5th. We're adding. And all those things, as you get, deeper and deeper into math, you always want to have sort of examples in your mind. You know by now that if you multiply these two together, it's really an x times an x times an x times an x times an x, and exponential notation says that's x to the fifth. So you added the exponents. So if there's any question in your mind, think about some numerical example or some simple algebraic example that reinforces the rule so you don't, make a goof. Okay, it's break time. Let's take 10 minutes and then we'll do some more. Prep for the exam. Start. Let's take a look at the other product of trig functions that we integrate. So sines and cosines are the easier one. We are targeting an odd power with the sines and cosines. With the tans and secants, we have two different options. We are hoping that the power of secant is even, and if the power of secant is even, we pull off secant squared. And if the power of secant is even and we pull off secant squared, we're still left with an even number of secants, which can be easily converted to tangents. The other strategy is to look for an odd power of tangent. If we have an odd power of tangent, we pull off a tan times a secant, put it with the differential. And let's just suppose if we did pull off a secant tangent for the differential, what's our u going to be?
Secant.
So the derivative of secant is what?
Secant.
So that would be the strategy. So if we pull off a sectan, we want to let u be secant because its derivative would be sectan. If we pull off secant squared, we're going to let u be tangent because derivative of tangent is secant squared. So this one we could do either. So let's go ahead and do it the secant way though, because there's going to be less conversion. So the 7 can come all the way out to the front at some point. We're going to pull off secant squared. So if we pull off secant squared, we're left with secant squared. And the secant squared that we pull off, that we sort of imagine as attached to the differential. Again, with the foresight, we're saying, oh yeah, we're going to let u be tangent because the derivative of tangent is secant squared. That means we want to get rid of these secants. So we've been calling these the leftovers. So we need to convert these leftovers. So these are the ones that were left behind. We want to convert them to tangents so that when we let u be tangent, we have a bunch of u's. Okay, so, oops, I don't think that's good. So if we want to convert those over, remember our strategy for this identity, the best thing you can do is get this little image memorized because it's such a good way to remember this identity. If that's tangent, if that's theta, this vertical line is tangent, and this horizontal diagonal here is secant, and this is 1 on the unit circle. That's the best way to memorize that identity. Tan squared plus 1 is secant squared. So if we replace secant squared, we just replace it with tan squared plus 1. So tangent to the 5th multiplied by tan squared plus 1 multiplied by secant. And now we are ready for u substitution. We let u be tangent of theta. Du will be secant squared of theta d theta. That's perfect. We've just got a bunch of u's and a du. And that's easily integrable. Power rule. We golden. So we'll end up with 7. Let's try to do this in one step. So if we plug in u for tangent, that's a u to the 5th. That's a u squared. So u to the 5th times u squared is u to the 7th. U to the 5th times 1 is just u to the 5th. And then secant squared of theta d theta, that should be an x, not a theta. This is going to be a du. So these are dx's, not d thetas.
And secant too.
And that one, yeah, thank you. All right, and that's an easy integral power rule, add 1, divide. So we will have 7 multiplied by u to the 8 over 8 plus u to the 6 over 6 plus Charles. Plus Charles. And then our u was tangent, so we just have to back substitute. So we're going to have 7/8 times tangent to the 8th of x plus 7 over 6 times tangent to the 6 plus c. All right, so that's how we integrate powers of tangent and secant. I've got another one on here, powers of tan and secant.
That one's fun.
That one is going to be done the same way. We'll pull off a secant squared and convert the leftover secant squared. We can come back to this. I want to make sure we get to some of this harder stuff, like trig sub. We can come back to that other one if we need to. Okay, so trig sub. Trig sub usually is for integrals that have sums or differences of squares. That's when we think about trig sub. That's the power of trig sub. Sum or difference of squares. So we look down here and we say, oh, there's a difference of squares. So that means trig sub is going to be the best strategy. On the exam, I tell you, use trigonometric substitution. But if in general you're not told, that's what trig sub is generally for. Power, differences in sums of squares. All right. So we prefer to have our sum or difference of squares with a 1. In this case, we want to factor out that 196. So that 196 is in the denominator, and it's inside of a square root. And we want to factor it out. So we're going to think about multiplying this x squared by 196 over 196, and then factoring that 196 out right there. And what's the square root of 196? 14. So that 14 is coming out to the front in the denominator. So that 196 and the square root is attached to it. So when it comes out with the square root. So the square root of 196. And then what's left in here is 1 minus. And what's going to be this next quantity that's going to be squared?
X over 14.
X over 14. All right, so that part that's left here, this x squared and this 196, we want to write that as a quantity squared. So the numerator 196 there, that came out with this other 196 in the bottom, in the denominator. But then what's left, x squared over 196, that's what's going to go in the parentheses. So x divided by 14, quantity squared. Now we have it like we want it. Now we have it like we want it. So trig sub, there's three substitutions. Sine, secant, or tangent. We know it's not tangent. Tangent's the plus. T looks like a plus. So it's either sine or secant. So this one is going to be sine. When we have a difference of squares with a leading one, we use sine. Because we know that 1 minus sine squared is cosine squared. Right? That's the whole point. 1 minus secant squared is not an identity. 1 minus sine squared is an identity. 1 minus sine squared is cosine squared. So difference of squares with a leading one, we are going sine. So we are going to let sine of theta be x divided by 14. We differentiate both sides. We get cosine of theta d theta equals 1/14 times dx. And now we can substitute. If you need to, you can, isolate the x if it's easier for you to write this before you do the substitution as that. You can, you don't have to. Same thing down here. If you want to isolate the dx, you can by multiplying by 14. Doesn't matter. So let's see what we end up with. So 1/14 integral x squared. So we isolated the x, then we square it. We're going to get 14 squared times sine squared.
Which is the 196 we started with.
which is the 196 that we started with, but one of the 14s will cancel, so we'll have a little bit of simplification. Oh, and there's another 14 actually. dx is going to be 14 cosine of theta d theta. We have all that. So does everybody see where all those pieces are coming from? So x squared, we square that. Isolate this for dx, we multiply both sides by 14 and we get that. All good? And then in the bottom, we have the square root of 1 minus sine squared. All right, so everyone cool on where everything came from? 1 minus sine squared is cosine squared. The square root of cosine squared is cosine, usually. And we have to remember, they don't tell us here that we are, on an interval where cosine is positive. So like we know in general that the square root of x squared is not just x, it's actually absolute value of x. Because if x is negative, and they don't tell us, and we just assume. If they don't tell us, the square root of cosine squared is cosine, square root of sine squared is sine. If they don't tell us, we just assume best. We assume best case scenario. So that tells us then that this all in here, the square root, that's all equal to cosine of theta. So that's just going to wipe out the cosine in the numerator. So this cosine right here is going to cancel with the entire denominator. All that's going to go away. Clearly one of the 14s is going to go away. So we're going to get 196 out in front, and we're integrating sine squared. And what is the strategy for an integral of sine squared?
Power reduction.
Power reduction. Reduce that power.
Integration by parts.
Or, if you're Lincoln,
Get help.
you can integrate by part. Let u be sine and let dv be sine. So sine squared, we have 1/2 minus 1/2 cosine of 2 theta.
Hey, if you just do integration by parts, you don't have to memorize the power.
Yeah, that's true. True that. So the division by 2 can come out in front. So we're going to get 98 out in front, and then we integrate 1 with respect to theta, and we get theta. We integrate cosine and get sine of the same angle. The angle can't change when you're differentiating or integrating. And then we use the reverse chain rule. Now, we are going to have to convert back to the original variable. The original variable is x. This substitution here allows us to create a triangle that reflects the relationship between the theta and x. So we have that sine of theta is x over 14. We always draw this triangle as if it's in quadrant 1 of the unit circle. Sine of theta is opposite over hypotenuse. So that represents the let statement, or the substitution statement. X over 14. Question?
Can you substitute at that sine squared theta? Can you substitute there?
No.
No.
We've got to wait. If you substitute there, if you substitute for sine squared of theta, you also have to substitute for d theta. It's going to bring you right back to where we started, right? It's going to undo what we just did. So if you did try to substitute before you integrated, then you'd get back to where we started. I mean, it looks tempting, but you have to remember you also have to replace the d theta, which is what's going to make the integral come back to haunt you. So what is the missing side here with the Pythagorean theorem?
196 minus.
That. Okay, now this triangle is based on theta, not 2 theta. In here we have a 2 theta. So we need to get rid of that because we have all our trig functions here, sine of theta, cosine of theta, tangent of theta, we have all single thetas. So that sine of 2 theta has to go bye-bye. So we are going to rewrite that with the double angle identity for sine. The double angle identity for sine says that sine of 2 theta is 2 sine 1 theta times cosine of 1 theta. And these 2's will cancel. So that identity is super important for this test. Sine of 2 theta is 2 sine cosine. Now we can convert back to x because we can use that triangle. And we can say that this is 98. So theta, let's think about that for a minute. So we started with sine of theta is x divided by 14. So what does that make theta equal?
Inverse sine of x over 14.
Yeah, that's right. Inverse sine of x 14ths. So that's going to be the first part down here. And we are going to distribute the 98, so let's just go ahead and do it now. So that's going to be 98 inverse sine of x divided by 14. Minus, and if we distribute that 98, we're going to get 98 multiplied by sine of theta, x over 14, and then multiplied by cosine of theta, which is adjacent over hypotenuse, so we're going to get the square root expression over 14 plus c.
Which simplifies to over 2 because
So let's see, so that simplification. So it's going to be let's see, what is that?
well that's 196 divided by 2 is what your 98 was, right?
I forget.
Yeah.
Yeah, 196 divided by 2. Yes, I agree. So it's going to be, totally agree. That's a good way to think about it. So then that's a 1/2 x times the square root of 196 minus x squared plus c.
Because that's how we got the 98.
Yeah, that's right.
Was
Yeah.
196.
196 over 2. So the 196 will wipe out the two 14s. Yeah, that's a great way to. What are they doing out there? It's not spring break yet.
Partying. What did you?
Yeah, see you.
That's the leading one is
Any questions on any steps there? Trig sub. So the hard part of the test, trig sub and improper integration. Those are the two pieces that tend to be the sticking points. We'll do a couple more trig subs though first. So another difference of squares is this going to be sine or secant? Secant. So when we factor out that 400, we're going to have a difference of squares with a trailing one instead of a leading one. So we're going to factor out that 400 because we like to have a 1 in there. It makes our life easier in the long run. We have to do some arithmetic in the front though. So that 400 is coming out, and when it comes out, the power is attached to it. So let's just write it with the 3/2 power for now. We'll simplify it in a minute. Okay. And so what's left in here? Let's see, we factored out 400, so that second part is just a 1 now. And there's no 400 in the x squared, but what we've seen is that if you pull something out when it's not there, what it does is introduce that quantity in the bottom, in the denominator. So this is going to be x squared over 400. So we're going to think about a 400 over 400, and then we're going to write this as x divided by 20 quantity squared. So now it's all factored out. We've got a trailing 1. We know we're going to use secant. So we're going to take that x by 20, x divided by 20, we're going to replace it with secant of theta. And again, if you want, you can isolate the x, because we know we're going to have to substitute in the x. You can usually just see it, but if you want to do it, totally fine. Whatever works. Whatever is going to make you make less mistakes is the best way to do it. You gotta kind of figure out where you're tempted to make mistakes and try to avoid those pitfalls. All right, so out in front, the square root of 400 is 20. Remember, we do the denominator first. So square root of that is 20, and then we have 20 cubed. Let's just write it as 20 cubed for a minute.
So we're gonna get at least 120 from the dx.
Exactly. We know we're going to cancel at least one of them. So we see the dx, and probably, I guess there's nothing else up there but the dx. So we have, that should be a theta. So we have 20 secant theta, tangent theta, so that's the numerator. So there's the dx. And then denominator, we have secant squared minus 1. And secant squared minus 1, tan squared. That was the whole point. The whole point was that we wanted to combine. We want these two terms in here to be mushed into one. And that's what trig sub does. If we do the trig sub, it allows us to turn the denominator into a single term, which then we have a lot more flexibility when the denominator is one term. Okay. So 1 over 400 in front, one of the 20s cancels. And then what is this denominator simplify to? Tangent to the third power. Everyone okay with that? You multiply the exponents, power to power multiply. So one of those tans is going to cancel. So that gives us secant, oops, I forgot the 400. Secant over tangent squared, theta, 1 over 400 out in front. Okay, so we have secants and tangents. And what we've seen is if we have secant to an even or tangent to an odd, there's something we can do. Well, that's neither. If it is neither, there are two choices. Immediately go to the Pythagorean theorem or convert everything to sines and cosines. The Pythagorean theorem here would only help us in the denominator, and that would make more terms than one term, which is almost always bad. You usually prefer to have less terms in the denominator instead of more. So that means going to sines and cosines makes the most sense. So let's go with sines and cosines. Secant is 1 over cosine of theta. Tangent is sine squared over cosine squared, but then we're going to flip it. So we're going to get cosine squared over sine squared. So we got that. Okay, one of the cosines is canceling, so this is perfect. That cosine is an odd power already. What do we let u equal? Sine. If we let u be sine, cosine is right there. Already tagged with the differential, so we're going to end up with a 1 over u squared. So if we're going to let's come over here and let u be sine of theta. So then du is cosine of theta d theta. That's going to give us an integral that we can calculate pretty easily. So we're going to have u to the negative 2. We want to pull it up into the numerator. U to the negative 2 du. U squared in the bottom is a u to the negative 2 up top. Change the sign on the exponent and it moves it. Moves it back and forth. So then we integrate, add 1 to the exponent, and we get u to the negative 1. Divide by the new exponent. makes everything negative. So we end up with negative 1 over 400 u,
Which is sine.
which is sine
So
Okay.
it's negative cosecant.
So we could write it as negative cosecant up in the top if we want. So now we're back to thetas, but we've got to get all the way back to x. So we're going to use our x over 20 as secant and build our cool triangle here. So always build this triangle the same, like it's in quadrant 1, theta goes there. And I already forgot what secant was, x over 20. So secant is hypotenuse over adjacent. And then we have one missing side, which we find with the Pythagorean theorem. Square root of
X.
hypotenuse first, so x squared minus 400,
Which looks right because it's what we had.
which is what was in the original, which is a good indicator that we're on track. And then we have minus 1, let's write it at minus 1 over 400. Sine of theta, opposite over hypotenuse, but it's in the denominator, so we're going to flip it. So we could do hypotenuse over opposite, which is cosecant. So hypotenuse divided by opposite looks like this.
Making sense.
There is the antiderivative we've all been looking for the last 15 minutes.
Full page.
Yeah. Calc 2 problems are long. They're longer than Calc 3 problems usually. Calc 3 is going to be so easy. I pray. Right, one more trig sub, and then let's do some improper, or maybe we'll do a little PDF, PFD.
But Tony said that and it doesn't make it sound very easy.
What?
He said it's like, oh, it's way easy.
Yeah,
Says the person with the master's degree.
exactly. Says the person who's taught it 40 times.
Yeah,
It's silly.
exactly.
You'll be
That's
fine.
his job. His job is to commute to us.
You'll be fine. Calc 3, come to the Math Center if you get stuck in Calc 3 so I can do some Calc 3 with you. I'll be in the Math Center a lot next semester. Okay, last trig sub, sine, secant, or tangent.
Tan.
Tangent plus is tan. So we're gonna pop out the 81, and the 81 is coming through a square root. So it's gonna be a 9. Remember, it's in the denominator. And then we have x squared over the square root of 1 plus x over 9 quantity squared dx. That make sense?
Yep.
So if you have to, hopefully you can see it by now, but if you don't, that's okay. Just, scaffold it. If you need it scaffolded, then just put in the 81s there. That's the 81 that's going to factor through and come out as the 9. And then this x squared over this little 89 in the denominator there becomes a square. If you have to draw that, that's totally fine. So then we said tangent. So that's x divided by 9 is tan of theta. So 1/9 dx will be secant squared of theta d theta. And then we're going to convert. So, and if we just go straight across, all the constants will work out. You don't have to try to be fancy. X squared is going to be 81 tangent squared. And then the dx, isolate the dx, we're going to get 9 secant squared. And in the bottom, we have 1 plus tan squared inside the square root.
Secant.
1 plus tan squared is secant squared. And then the square root of secant squared is secant. So let's not write all that. Let's first write it like that. So 1 plus tan squared is secant squared. So we'll end up with 81 out in front in the numerator. These 9s are going to cancel. And we end up with tangent squared times secant. Once again, we have powers of secant and tangent that don't match our little tricks. Tangents not to an odd and secants not to an even. So if we have a situation like that, we have two choices. Convert to Pythagorean right away, convert with the Pythagorean right away, or turn to sines and cosines. Doesn't really matter. This looks very easy to convert over. So this would be tangent squared, that's the vertical, so we have to do secant squared minus 1. This looks very unpleasant.
Yeah. Well,
So-
part of it's easy. Negative.
Part of it's easy.
We've done secant.
We've done secant. We have done secant cubed twice. So we get that. All right, so we're gonna, let's separate this. So this is gonna be 81 multiplied by, let's separate this into two integrals. And then let's talk about the first one for a minute. Because you definitely need to know the second one. This second one shows up a lot. How do we integrate plane secant?
Natural log of secant theta plus tangent theta.
Exactly. So this is minus natural log absolute value secant plus tangent. So we did that one a fair amount earlier on. How do we integrate this one? So we did it two different ways.
Well, you could do, what's it called, parts with secant and secant squared.
Yes. So that's the way, that was the primary way we did it back in 8.2 or 3. I'm not gonna like hide an integration by parts in the middle though. So if you come back, so that you would have to do integration by parts. I don't want to go through that right now. We don't have a ton of time. So if you come back to chapter 8, integration by parts right here. Here is where we first did twist. Here it is, right there. Secant cubed using integration by parts. It's kind of, we're not going to do this. I'm not going to give you this inside of another problem. That would be brutal. Except maybe I'll give it to Zach. Zach, you get a special test. You're going to integrate secant cubed. No, I won't do that to you, Zach. Okay, so that's how you would do secant cubed. And then integral of secant, remember back here in 8.1, when we looked at miscellaneous, let's see, or was, I think it was, does anyone remember where we did secant originally?
I think, did we do it in the start of integration by parts or something like that?
What, is that where it was?
Maybe I'm crazy.
I could have sworn it was earlier. Maybe it's at the very, oh, here it
Oh,
is.
there it is.
Page 1. So remember that to integrate secant, if you look at the integration tables, we recognize that sine and cosine go to each other essentially, and the other four are all logs. So tangent, cotangent, secant, and cosecant are all logs. And so the trick was that we had to multiply by 1 to put it in that log form that we've talked about. And if you multiply by secant plus tangent, you see that the derivative of secant plus tangent is the new numerator, so it's in log form. So that's the one that we see a lot. So know that one. Okay, back to more math. Let's see, PFD. So let's just write the triangle. We're not going to finish this one, but at least let's make sure we understand the triangle. tangent of theta is x divided by 9. So when we draw our triangle, we're drawing this. Tangent is x divided by 9, so that's opposite over adjacent. And what will that make our hypotenuse?
81 minus 81 plus x,
81 plus
x squared.
x squared, yeah, exactly. So when we look over here, where we have this secant plus tangent that has to get replaced, we're going to use tangent, of course, is x over 9, but secant is going to be the square root expression over 9. That'll be secant. So that's how you could finish it off. PFD. So PFD, again, I will tell you on the test so that you're not spinning wheels trying to decide whether you should use PFD or trig sub or something. So I'll tell you. So the concept, though, behind PFD is that you can factor the trinomial in the denominator. So if you have a trinomial that you can't factor, we completed the square. If you have a polynomial that you can factor, then we factor it. And this one will factor into x minus 5 times x plus 3. We've got that. And PFD is the process of breaking apart a rational expression into partial fractions. So this fraction here has a quadratic in the denominator. We want to break it apart into two fractions that have linears in the denominator. So that's our strategy. So we're going to take our fraction, and what we're going to do is sort of set up the form that it must take. So it must have come from something over x minus 5 plus something over x plus 3. And going from the right side to the left side is what you do in college algebra. You combine rational expressions, get a common denominator, mash it all together, and you get that thing there. Calc 2, PFD, we want to bust it apart because those are easier to integrate. Those are both logs. So that's why we do it. All right, so we multiply both sides by the denominator on the left. And when you multiply by that denominator on the left, you're going to end up with this. And that is our PFD equation. And that PFD equation, we can solve for A and B in a couple of ways. The simplest way is the convenient value method. And what are the two convenient values? So the convenient values are the numbers that cause zeros in either of those two factors. That PFD equation is supposed to be good no matter what x. Doesn't matter what x you plug in. So in particular, if you plug in x equals -3, it has to be true. And if you plug in 5, it has to be true. So let's plug in -3. So when we plug in -3 right here, that goes away. And this becomes -8 times b. So this allows us to find b really fast. And similarly, it's true for all x. In particular, it's true for x equals 5. So we're going to get 3 equals 8a. So a is 3a's. So now we have the PFD constant solved for, which allow us to go back to the integral and rewrite this as the integral, still 0 to 2, that hasn't changed. But this fraction has now become 3/8 divided by x minus 5 minus 3/8 over x plus 3 times dx. And now we're golden. Those are both logs, right? We know the integral of 1 over x. Well, these are just shifted, and that's not hard. So this is 3/8 natural log, absolute value, x minus 5, minus 3/8 natural log, absolute value, x plus 3. 0 to 2. And let's see if we get any simplification here. Plugging in the 2, we're going to get natural log of 3 minus 3/8, natural log of 5. Subtract off what we get when we plug in 0. So minus 3/8 natural log of 5. Plug in 0 there. Minus a minus is plus 3/8 natural log of 3. Okay.
Could you have just put them in fraction?
We could have done that too. We could have created a fraction right away with a log property. Now we'll combine it with a log property anyway. So you could have done it before or after.
If you're gonna combine them, does the 3/8 have to be in the exponent as well, or no?
Well, you could factor it all the way out to the front
Oh,
because they
right.
happen to have the same coefficient, which would be convenient. So you could use log properties right now, and you can combine those two with a log property, and you can combine those two with a log property. So, I mean, now we can just add them though.
Yes.
3/8 plus 3/8 is 6. Well, I guess we can finish it off. We're almost there.
3/4.
Yeah, might as well finish it since we're this close. So log 3, so these two, we're gonna get 6/8, which is 3/4. Log 3. These two we're subtracting, so you can factor out the minus, and you're gonna have 3/8, or you can just think of it as subtract, doesn't matter. So minus 3/4 log 5. So. And if you wanted, you could go one step further and you could factor out the 3/4 and write it as natural log of
3/5.
3/5. So either of those is fine. Either one. Okay, let's go to, there's a couple more PFDs here. If you're getting stuck on those, just post into our question area up here. Just post up here somewhere and I'll be looking for the next couple days for sure. So let's get to improper integration because that's the next hardest thing. So improper integration, the most important slide with improper integration is this summary slide at the very end of chapter 8. So this summary slide shows us the function 1/x. 1/x is the black curve. And we know that this vertical tail for 1/x is infinite. And we know that the horizontal tail for 1/x is infinite. And it's the threshold function. Any curve that's closer to the axis is going to be finite in area. Any curve further away is going to be infinite in area. So this red one right there, that's definitely infinite because it's more area than the 1/x curve. This is going to be finite because there's less area than the 1/x. And similarly down here, 1/x, this is infinite, which makes the blue underneath infinite, and it makes the red, oh, it took that properly, I guess. And it makes this finite. Okay, so that's kind of our threshold. So in our mind, we are thinking this. If the power on x in the denominator, if it's more than 1, we have finite here and infinite there. That's the red one. If in the denominator the power on x is less than 1, it's reverse. It's whack-a-mole. Now this is going to be this is going to be infinite under the blue, infinite. Blue, that's smaller than 1, infinite. But over here, it's going to be finite. So when the power on the x in the denominator is less than 1, it's finite vertically and infinite horizontally. And vice versa if the power is bigger than 1. So you've got to have that in our mind. So when we look here, the math should just confirm what we know. The power on x here is what?
Less than 1/2.
It's less than 1. The power is 1/2. The square root of x is x to the half, so it's less than 1. So the horizontal tail should be infinite, and the vertical tail should be finite. Okay, so this is a horizontal or vertical tail. 11 to infinity. Horizontal tail. So in our mind, we should already be saying, oh, this is going to be infinite. right? And that helps you to not screw up the limits at the very end when you know what you're supposed to get. Right? It's very easy to mess up limits, and if you know what you're supposed to get, that helps. So the first thing we always do with an improper integral is write down limit. And usually for horizontal, we're going to go limit as b goes to infinity. And then we're going to chop off this integrand, so we're going to go from 11 to b instead of 11 to infinity. We're going to write this with a negative exponent, and that's going to allow us to integrate it. So the limit, we just let it sit out in front. We add 1 to the exponent, we divide by the new exponent, we evaluate that on the interval. So add 1 to negative half, get positive half, divide by half is multiplied by 2. You can factor the 2 all the way out in front if you want. You could leave it in there, it doesn't really matter, it's your choice. So the 2's coming out, we plug in the b, square root of b, right, b to the half, square root of b, minus the square root of 11, and this is as b goes to infinity. And what is that limit equal to? Infinity. Oops. So that's infinity because the square root of b, that's a bird wing, and that's going up forever. Right? Square root of a number that's getting bigger and bigger is going to get bigger and bigger. So the limit is going to be infinite. That's what we expected. Any questions on any of the steps there? All right, let's take a look at this one. Okay, so first, is it a horizontal tail or a vertical tail? Horizontal tail because we see infinity in the limit of integration. If you see infinity in there, it's always horizontal.
Unless you're getting dy's.
Unless you're converting the variables. Good point. So we're going to do the same thing. We're going to introduce limit as b goes to infinity of 2 to b 9 over x ln x. Now, what is our hunch? So this one's a little, or not in terms of converge or diverge. Do we think the tail is finite or do we think the tail is infinite? So we normally are looking at the power on the x. But this denominator doesn't just have x, it has x ln x. So it's a little bigger than just x. It's not as big as x squared, but it's definitely bigger than just x. X times ln x, right? Ln x is bigger than 1 after you get past 1. So it's a little bigger than x. And the answer, well, we'll find out if we're not clear in our minds yet, but we probably suspect that it's going to converge, that multiplying by ln x is probably enough of a bump on the x. So let's check. So what is so I heard a u substitution. What should we let u be?
Natural log x.
Natural log x. And so this u substitution is only going to work if the derivative of u is somehow present. And oh yeah, there it is, right? There is the derivative of ln x, dx over x.
Isn't this just log form then?
I'm not seeing it in log form.
Right? Because it's
Oh, I guess if you are clever, it is in log form. You could shove that x up into the numerator and make it 9 over x. Yeah, you could do that. Yep. So
weirdest log form.
we'll just assume that I'm
It's a
not
log
clever.
But
So this is going to be the integral of 9. So I said that u was going to be the natural log of x, then du is, so it looks like that. Let's just put in placeholder limits. We'll come back and convert our limits in a minute. So there's just plain old u sub. If u is natural log of x, it goes in the denominator, the x in the bottom and the dx in the top, that's this, becomes du. So then this is going to be 9 natural log absolute value of u. These are placeholder limits until we get back to the x. So So let's see, limit still just lingering, waiting to be invoked. So we have 9, natural log, absolute value of u is natural log of x. And our x limits were 2 and b. So we have that. So this is limit as b goes to infinity. It's not looking good for the convergence. So the 9, let's pull that 9 all the way out in front. It's easier to evaluate limits if there's not any extra junk in there. So we're going to have natural log of b minus natural log of 2. So we're taking that whole limit as b goes to infinity, and that is infinity. Darn, didn't converge. It wasn't enough. So it definitely had a little bump on the x, but not enough.
And so anything that goes to infinity times x will go to infinity in the bottom? It's just like if it has an asymptote, it
It
won't.
depends on how fast it goes to infinity.
Okay.
Depends on how fast.
So if it was going really slowly to infinity, it might not.
Right, like this one's, the natural log's going to infinity just a little too
Faster.
slowly. Yeah. All right, any question there? So XL and X, so we multiplied by natural log of X and it wasn't quite enough. It wasn't quite as much as X squared. We know X squared would have a horizontal tail that's finite.
You can
Not quite enough.
You can get rid of the absolute value when you start substituting because it's
Because we've got the,
Ln of x is always positive.
yeah, so here the B and the 2 are positive.
Oh,
So
gotcha.
is that where we're looking?
yeah.
Yeah, so we don't need it there anymore.
Oh yeah, so if you have limits that make it so that your range is always positive, it doesn't matter.
Then it doesn't matter.
That makes sense.
All right, let's try another one.
Ln of ln will always be positive.
Ln of ln will always be
Ln is
positive
positive.
if you're on that interval. Pass 1. Okay, so what about this one? Horizontal tail or vertical tail?
This is a vertical.
Vertical tail. So these are more deceptive. You don't see the infinity up in the limit of integration, as a red flag saying, hey, I'm improper. This you can't tell. So here you have to be you have to be thoughtful and say, oh gosh, this integral is not a definite integral. Like in Calc 1, you're kind of, you sort of are led to believe that as long as the limits are numbers, it's a definite integral. But a definite integral also requires that the function on the inside is continuous at that point. It's not continuous at 7. So this has a vertical asymptote at x equals 7. So once we recognize that it's improper, we know that we have to use a limit. Usually for the vertical ones, they use a c, so we'll say c is going to go to 7. And now we have to make sure we indicate what direction we are approaching the 7. So we have to decide, we are approaching it from the right or the left? From the right. Is everyone clear on that? Because our interval is 7 to 8. So if we're looking at the number line, there's 7, there's 8. The interval that we're integrating through is right here. So stuff to the left of 7 is not included. So we're coming into 7 from the right-hand side, from within the interval. So 7 from the right. And then we do what we always do when we have something in the denominator, we just bump it up to the numerator, and that makes it easy to integrate. So that will become that. And limit, again, we're not going to evaluate that for a while. We can just write it as LIM. We know that we'll put the C later. So integrate here, we add 1 to the exponent. So we add 4 over 4, which leaves us with negative 1 over 4. Divide by negative 1 over 4 means multiply by negative 4. So we're going to take the limit of all of this. That's from C to 8. Now we can do our evaluation. We can pull that negative 4 all the way to the front. It's just a little easier to clean out those constants. Plugging in the 8, that tells us we're going to have 8 minus 7, which is 1 to the negative 1/4. 1 to any power other than, I guess 1 to any power is 1. There's no exceptions. 1 to any power is 1. And then we plug in the c, and we're subtracting. And I factored out the -4, so that's out here. So we subtract off, that's going to be c minus 7 to the negative 1/4. And that limit is as c goes to 7 from the right. So this is going to where?
Negative infinity to 0. To 0.
So that one term, so let's try to rewrite this. Let's maybe write it like this, just so it's more obvious what's happening. If you get rid of the negative exponent and put it in the denominator, it's going to look like that. So as c is going to 7 from the right, tell me this. Is c minus 7 positive or negative or either?
Positive.
Always positive, right? Because you're coming into 7 from the right. 7.1, 7.01, 7.001, etc. So this is always positive, okay? But it's going to 0, so this part here is going to positive or negative infinity. Positive infinity. And then we have 1 minus positive infinity, which means this whole piece is going to negative infinity. But then we multiply by -4,
And you get positive.
so we get back to positive infinity. So the whole thing will be going to positive infinity. And we are finding area, so we should end up with a positive. And that is what we expected, right? Because this exponent on the x is bigger than 1, but it's a vertical tail. Bigger than 1 on the x for a horizontal tail is finite. Bigger than 1 on a vertical tail is infinite. So that's what we expected to get infinity there. All right, let's try one more improper integration. So find the volume of the solid x to the -5 on that interval. So our basic look of this thing, we have this decaying function like that. It's approaching 0. And we are looking on the interval from 2 to infinity. So let's suppose that's 2. And we're trying to find all this area here when it's rotated around, or find the volume when this is rotated around the x-axis. So if we go around the x-axis, we're going to pick a random x here. And what shape is going to be created when we rotate that around the x-axis?
A washer, or a shit, a washer.
A degenerate washer, which is a disk. A washer with no hole in the middle. So that area will be pi times the radius squared of our disk. And what is playing the role of the radius here?
X to the -5.
X to the -5, yep. So this is going to be pi times the radius is the function, x to the -5, and that's squared. So we're going to get pi times x to the -10. Multiply the exponents. So that tells us the area of the disk at x. So depending on your x value, whatever it is, you plug it in there and you get the area of that little disk. The volume is found by integrating the area. So we're going to integrate x to the -10 from 2 to infinity. That's a horizontal tail. Is that going to be finite or infinite? finite because the power in x is bigger than 1 in the denominator, right? It's a 1 over x to the 10. And right away, remember, we have to write limit. As soon as we recognize that we have an improper integral, we've got to write limit. And usually we're going to go 2 to b. We're going to let b go to infinity if we're dealing with a horizontal tail. That's x to the negative 10 dx. Limit's coming along for the ride. Do this definite integral first. So we add 1 to negative 10 and get negative 9. Divide by negative 9 from 2 to b. Let's factor out that negative 1/9 all the way to the front. Okay, so now let's plug in the b. So we took out the negative 9. All we have is this x to the negative 9. So it's b to the negative 9, which we'll write as 1 over b to the 9. It's always easier with no negative exponents when you're evaluating a limit. Minus, negative 9 is gone, so now 2 to the negative 9 is 1 over 2 to the 9. It's just a constant. So we're going to evaluate this as b goes to infinity. Where does this fraction go as b goes to infinity? 0. That denominator is growing without bound, so those fractions are shrinking down to 0. And this tells us that our final answer is a negative times a negative, which is positive. We're going to have pi divided by 2 to the 9th times 9.
Also, it should be b to the 9th on the last one.
Oh, where I wrote b to the 6th. Thank you.
It doesn't matter. It'll
No,
still
it-
either way, but for clarity's sake.
Yeah, it doesn't matter in terms of what the limit becomes. Yeah, b to the 9. So finite, as we expected.
A very small amount though.
A very little bit of volume. Volume? Yeah, volume. A very small volume. Small volume.
Anything divided by 2 to the 9th is a small amount.
So we have 3 minutes. Let's do one separable differential equation. We'll have time to do one here. So this says dy dx is equal to e to the x minus y. And the first thing we're going to do is rewrite it as e to the x times e to the minus y. So what we want to do is to try to create multiplication where we have all the x's together and all the y's together.
Would it be easier to write it as e to the x over e to the y, just because then you have 2 fractions instead?
Absolutely. If you want to write it in the denominator, if that's easier, 100%. Either way, when we move those y's to the left, you're going to end up with that. Whether you think of the e to the y in the denominator and you multiply it to the left, or whether you think about just multiplying by both sides by e to the negative y right here. I mean e to the positive y. Duh. And if you multiply by e to the positive y, this all becomes 1. So once we've done that, now is where we integrate. And we're integrating, the interesting thing about separation is that you're integrating each side with respect to its own variable. And so on the left, we are integrating with respect to y. On the right, we're integrating with respect to x. So that is an implicit general solution. And what do we have to do to both sides to get to the explicit general solution?
Log.
So if we just take the natural log of both sides, we now have the explicit general. Up here we have the implicit general. And we always want to get to the explicit if we can. So that is where we want to end up. All right, well, let's stop, and if you have questions, I'll be in the Math Center today. I'll be here after class today. You can post it in OneNote, email me, whatever
Do you need the absolute value on the index plus C? Because
Separated.
That is gonna come out in the wash. If we were to find a particular C, it would have to be, this part's always positive, right? So when we find our particular solution,
Must always be greater than.
it's got to be,
Or
yeah,
greater than -1.
correct.
It's negative.
All right, good luck studying over the next 48 minus 3 hours.
You've been caught up.
What's in the math lab tomorrow? Is there anybody?
I'm in the math lab tomorrow, I'm somebody.
Are you in there tomorrow?
I'm in there
What's your-
tomorrow from 9 to 11.
9 to 11?
9 to 11. Does that work for you, or? Oh, good.
Yeah.
you said homework's due tomorrow.
Tomorrow midnight, homework and quiz, tomorrow midnight,
And you'll have,
not tonight.
when will you have the worksheet done? You're gonna do it during the test?
I'll grade it during the test.
So then,
That'll be the easiest. And then the correction should just be due by the end of spring break. Yeah. And you're gonna take it along, Mark? Okay. Say again?
Well, it's all this.
Oh, okay. Sounds like a plan. Where is this? There it is.